Hello there. This is section 10.2, which is plane curves and parametric equations. Again, I apologize for my nasally voice. We'll start off this section by considering this illustration here, which entails an object that is being thrown into the air at an angle of 45 degrees. It tells us that the initial velocity of the object is 48 feet per second, and this travels in a parabolic path. Well, in the past, we are often referring to the parabolic shape as a rectangular equation. A rectangular equation involves x's and y's. But now we're interested in something called a parametric equation, which takes into account time, which is very important. So what we're going to do in this section is we're going to take these rectangular equations and convert them to parametric equations, which again involves time. So to determine this time, what we're going to do is introduce an additional variable, t, and that's called a parameter. So what we're going to do is we're going to write both equations, both x and y, as functions of t. So what we'll have when instead of one rectangular equation, we will have two parametric equations. One for x, which involves t, and another for y, which also involves t. And again, this takes into account time. So now that we have these 2 points, at a time of 0, so if t is 0 and we plug in 0 into those previous equations, we'll find that the corresponding point is 0, 0. Likewise, at a time of 1, I can find the point of the object to be right here. And this is found simply by plugging 1 in for t into the equation for x and the equation for y. And this goes on and on. So this is helpful when we are dealing with different motion problems, and the resulting path is called a plane curve. And the definition of that is here. So again, we will have two functions, one for x, one for y, and they're both in terms of t. So these are known as parametric equations, and again, t is the parameter. And we'll have a set of points, x and y, which I kind of explained up here. Okay. When you are sketching a curve, you basically plot the points on the xy plane. And the coordinates are determined by whichever value you choose for the parameter t. We'll also want to identify the orientation of the curve, which basically indicates what is the direction of the curve. And so in order to determine that, you'll start with the smallest value of t and then plot the points as t increases, and that will tell us the direction in which the curve is going. Let's look at a quick example. Here in this example, it says sketch the curve described by these parametric equations. So here we can see what x is. X is this in terms of t, and y is this in terms of t. And we are only interested in values of t from -2 to 3. So the solution here is found by taking these values on the interval of t and simply plugging those values into the parametric equations. So when t is -2, we will have this ordered pair. When t is -1, we have this ordered pair. And again, these values are found simply by plugging the value for t into the equation for x, so finding f of -2, and then g of -2 to get this ordered pair here. So on and so forth. Well, by plotting these points in order from increasing values of t, we can start by saying t equals -2. When t equals -2, we have this ordered pair. Then when t equals -1, we have this ordered pair, so on and so forth. And so these arrows are drawn in here to show that as t gets bigger, this is the orientation of the curve. Okay. Now, sometimes we want to do what is called eliminate the parameter. And when we eliminate the parameter, I told you before that the parameter is t. So if we're given a rectangular equation, sometimes we want a parameter in it. So we will take a rectangular equation and make it a parametric. But sometimes we're given parametric equations and we want to convert those to rectangular. And the way we do that is we need to eliminate the parameter, which is t. So what we'll do in order to do that, if these are my parametric equations, I will take one of them and solve for t. So I've taken this equation and I've solved it for t. Then what I'll do is I'll take this value for t and substitute it into the other equation for t, which is shown here. And then I'll simplify and you will end up with a rectangular equation. You know you are at a rectangular equation when t has been eliminated. So here, from our very first example that we saw, we end up with this rectangular equation. And this was the graph that we had, and we should be able to recognize that this is a graph of a parabola with a horizontal axis. Okay, so we can kind of see how this ties into the previous section. The range of x and y implied by the parametric equations may be altered to change to the rectangular form. So we need to make sure that we're using the same domain, but we need to alter it from t to x. So the domain of a rectangular equation needs to be adjusted so that it matches the graph of the parametric equations. So here is an example. It says write the corresponding rectangular equation by eliminating the parameter. So you can choose either equation to solve for t, but sometimes one is easier than the other. So what I'll do is I'm going to choose this equation here to solve for t. And in order to do that, what I'm going to do is I'm going to raise each of these to a power of 4. And I'll find that x to the 4th is equivalent to t. So once I have one equation solved for t, I will take that and plug it into the other equation for t. So this becomes y equals 8 minus x to the 4th. This here is my corresponding rectangular equation because there aren't any t's involved. The only other thing I need to do is identify the domain. The domain here is x is greater than or equal to 0, because if you look at the original problem here, the outcome of this will always be 0 or positive, no matter what the value of time is. So this is my final answer. Here it says use a graphing utility to graph the curve represented by these parametric equations. We need to make sure we identify the orientation of the curve and then eliminate the parameter. Okay, now the thing to recognize here is that our parameter is theta, not t in this case, because here we have trig equations, so we're using theta instead. So the easiest thing to do in order to graph this, and I can plug this into a graphing utility, but let's analyze this by hand. What we do is we always take the parameter, we pick some values for the parameter, and then plug them into the equation for x, and then plug them into the equation for y. So since I have some trig functions here, I'm just going to start with some of the basic values that are found on the trig, the unit circle. So I'm going to start with 0 for theta. If I plug 0 in for theta, cosine of 0, so this ordered pair here is 1, 0. Okay, so if I'm thinking of the unit circle, remember cosine are the x values, sine are the y. So this is 1. 1 times 3 is 3. And then negative 2. So that gives me a 1 for x. Sine is 0, so I end up with a negative 5. Then, if I have, let's do pi over 2. Pi over 2 on the unit circle is here. This ordered pair is 0, 1. So now cosine is 0, so this becomes 0, so x is negative 2. And then this is 1, so this is also negative 2. If I choose pi on the unit circle, this is where pi is on the unit circle. So this is negative 1, 0. So this gives me a negative 3 plus a negative 2, which is negative 5. This is 0, so this is also negative 5. Lastly, let's choose 3 pi over 2 on the unit circle. This ordered pair is 0, negative 1. Plugging those values in, I end up with this. Okay, so I have enough information to go ahead and sketch this picture. Okay, so I'm just going to go ahead and draw some tick marks. All right, now when I sketch this, I'm going to start with the smallest value of the parameter, which is 0. So I'm just going to plot this ordered pair here. When I plot this, I have 1, negative 5, which is here. Then when I plot the next one, pi over 2, I have this ordered pair, negative 2, negative 2, which is here. Okay, so I know that I'm going to go from here to here. All right, then the next one is negative 5, which is here-ish. Here, sorry. So we're heading in this direction. And then lastly, I'll have negative 2, negative 8, which is here. Okay, so it looks like this. And it's sketched here. Now, the other thing we want to do is we want to eliminate the parameter. Now, eliminating the parameter in the previous problem, we solved for t. Well, solving for theta is kind of tricky, and it will really complicate things. So instead, what I'm going to do is I am going to use a Pythagorean identity. In fact, I'm going to use sine squared of theta plus cosine squared of theta is equal to 1. Because this is the easiest one to deal with, and I already have sine and cosine. The thing I need to do is I need to get cosine of theta by itself and sine of theta by itself. So in order to get cosine by itself, I'm going to add 2 to both sides and then divide by 3. So cosine of theta becomes x plus 2 divided by 3. Similarly, to get sine by itself, I'm going to add 5 to both sides and then divide by 3. So sine of theta is equal to y plus 5 divided by 3. So here, I know what sine is, I know what cosine is, so what I'm going to do is I'm going to take these and plug them in here and here. So I have, let's see, y plus 5 over 3, this quantity squared, plus x plus 2 over 3, that quantity squared, and this is equal to 1. Okay, well, if I square the top and I square the bottom, I end up with y plus 5 squared over 9 plus x plus 2 squared over 9 is equal to 1. Well, looking at this, I have the same value in the denominators, so I'm just going to get rid of it. There's no need to have that, and I'm going to multiply everything by 9. Additionally, I'm going to write the x value first. So my final equation is x plus 2, that quantity squared, plus the quantity y plus 5 squared is equal to 9. And you should be able to see that this is the corresponding rectangular equation. And it is, in fact, a graph of a circle with the center of -2, -5, and a radius of 3. And that's what we have. Good stuff. Now here we are given a rectangular equation, and from this rectangular equation we want to come up with 2 sets of parametric equations. The cool thing about this is there are an infinite number of possibilities, because whatever you make x equal, then the y value will go along with that. So you can make x be anything you want. For example, I'm going to say let x equal t. Okay, well, if x is t, this is my first parametric equation. First of 2, x equals. Awesome. Now I need to find what y should be. Well, if x is t, then I just plug t in for x. So that means y is equal to 4 over t minus 1. Guys, I'm already done with one of my sets of parametric equations. Boom. That's the easiest to do, is let x be t. All right, well, let's find another one. Let x be something else involving t. You can make this as extravagant as you want. But sometimes people say, hey, let x be t squared. Let x be t plus 1. It does not matter. Whatever x is, you plug that in. So now we're going to plug this in for x and find y. Okay, so y is 4 over x, but instead of x, we have t plus 1. And then minus 1 from our equation here. Well, here, the plus 1 and minus 1 cancel out. So really, the y equation is 4 over t. Excellent. Here is my second of 2 sets of parametric equations. And I am done. Isn't that amazing? All right, here is the final example. Here it says find a set of parametric equations for the rectangular equation that satisfies these given conditions. Okay. Well, some people will choose to sketch a picture of this. You can certainly do that if you want. It's completely up to you. But just by observation, I know that this is a graph of a line. So when I'm done, I need to make sure that I'm dealing with a graph of a line here. Okay, so this given information here, let's just make our little chart. Okay, What this is saying is when t equals -1, we have the point -2, -7. Okay, well, cool. Now, what we need to do from this is we need to come up with some sort of equation because we need a set of parametric equations. Okay, so when we say I need a set of parametric equations, I need an equation for x and an equation for y. Well, like before, you can really pick anything you want for x, but we need to make sure that it falls in line with what we're dealing with. So let's go ahead and compare x and t. Well, if I want an equation for x, and I know that x is -2, how do I get from -2 to -1? Well, I can take t minus 1, right? Because x, this value, is t minus 1. So, it's really kind of by inspection. So my first is going to be x equals t minus 1. Okay, well, if this is x, I can find y by plugging it in here. So y is equal to 4 times the quantity t minus 1 plus 1. All right, well, let's rewrite this. So y equals 4t minus 4 plus this 1 on the outside, and this gives me y equals 4t minus 3. So I have these two equations that are my parametric equations. Not so bad. So from here, if I want to check my result, I certainly can. Remember, what I want to do is I want to solve this for t. So if I solve this for t, t is equal to x plus 1. And what I would do is I would take this and plug it into my other equation for t. So I will have y equals 4 times t, but t is really x plus 1, minus 3. Distribute this and rewrite this, and I get 4x plus 1. And this is the rectangular equation we started with, so it checks out. So one set of parametric equations is this right here. This wraps up section 10.2. Isn't this a lovely way to end a semester of calculus?